Hi, and welcome back to the YouTube video lectures for Chemistry 103. This particular video is focusing on writing and balancing chemical equations, and this correlates to Chapter 3, Section 7 out of your book. So a chemical reaction can be conveyed in symbols and numbers, and what we're trying to do when we write down a chemical equation is show exactly how many molecules and atoms and formula units of different compounds and species are present and how they interact with each other. So the first step to getting a good chemical equation is that we need correct formulas for each and every reactant and product. So we kind of have to think back to our last unit on how to formulate compounds formulas. For ionic compounds, for example, if you recall, we learned about how the compound has to be neutral overall. It can't have a charge associated with it. And it is made up of charged particles, of ions, but those cations and anions have to balance each other out. If we, for example, have two ions, let's say calcium 2 plus and chloride minus, we're going to cross over the charges to get the ratio of calcium to chlorine. And we need 2 chlorides for every 1 calcium. That'll give us a nice ionic compound with no charge associated with it. So that's definitely a key skill to bring to the table for this. We will sometimes you might be given a chemical equation with all the formulas already written out, in which case you might just need to balance it. Sometimes you might have to derive the formulas for all the reactants and products based on what you're seeing. Or maybe you listen to me say the names of the compounds and you have to translate that into formulas. So there's kind of a few different wrinkles that you'll see in writing down equations for chemical reactions. Just a couple new tips to this regard. When you have metals in a chemical reaction, if I say that copper reacts with hydrochloric acid to form copper chloride, copper 2 chloride, you should show the copper in that reaction simply with just the atomic symbol for copper. No subscripts. Metal atoms exist in metallic bonds, and so that they're kind of like ionic compounds. There's no molecules. They don't usually form groups. So we just represent that with the symbol for the element. Nonmetals, on the other hand, they do form these diatomic molecules. So you can see all of these nonmetals here, chlorine, oxygen, hydrogen, etc., have a subscript of 2. Reason for that is that these elements are just much more stable in these diatomic molecules rather than being lone atoms. A few exceptions to that second bullet point is that sulfur forms molecules of S8, and phosphorus forms molecules containing 4 atoms of phosphorus. So if you are trying to translate the words phosphorus reacts with chlorine gas to form phosphorus pentachloride, you would want to show the phosphorus in that reaction as P4. Okay, so let's do a little example. We'll start with a very familiar reaction, just the production of water from hydrogen and oxygen gas. So first of all, we should recognize that hydrogen and oxygen are in these diatomic molecules, and we should write them as such. And our formula here for water is correct, H2O. On an atomic level, let's look at what we have. We have 2 atoms of hydrogen in a diatomic molecule. We have 2 atoms of oxygen in a diatomic molecule. And then we have a molecule of water. Now what's wrong with the picture? The problem here is that, so let's count up our atoms here. We've got 2 atoms of oxygen, 2 oxygen atoms. We've got 2 hydrogen atoms. But then in our water molecule, we have 2 hydrogen atoms, but we only have 1 oxygen atom. So it's not like this reaction happened and an atom of oxygen just was destroyed. We need to show that these species, these molecules, react in certain ratios. Now, if we want to have a nice balanced chemical equation, really the way that they're going to react is 2 hydrogen molecules will react with 1 oxygen molecule to make the 2 water molecules. And you can see now we've got 1, 2 oxygen atoms on the reactant side, 1, 2 oxygen atoms on the product side, 1, 2, 3, 4 hydrogen atoms, 1, 2, 3, 4 hydrogen atoms. So this is how the production of water actually happens. This is the ratio of reactants to products. We can express that with these coefficients. So you see on this formula here, this equation, to express that we're going to have 2 of these diatomic hydrogen atoms, we use this coefficient of 2. There's no coefficient on the oxygen. When there's no coefficient, that means that there's 1 molecule involved. And then there's a coefficient of 2 on the water. So yeah, the ratios here, 2 hydrogen molecules for every 1 oxygen molecule, forming 2 molecules of water. Okay, so now moving on to how you go about that process, rather than drawing out lots of cartoons and trying to count up atoms. First thing to keep in mind is you can never, ever, ever change the subscript on a compound. It would have been really easy when we were just working with the production of water formula to change the formula of water to H2O2. But that just doesn't work because we end up with a completely new chemical, hydrogen peroxide, which is not water. Don't try to drink it. What we want to do is add coefficients to indicate the relative amounts of all of those reactants and products. So that's how we got that's how we arrived at that ratio on the previous slide. The way you would state this chemical equation, and actually this is backwards from the previous slide, but this is showing the decomposition of water into hydrogen and oxygen. The way you would state this reaction is every 2 moles of water will decompose into 2 moles of hydrogen and 1 mole of oxygen. You can use the terms moles and molecules kind of interchangeably, but keep in mind that you are talking about different things. If we're talking about individual molecules, we're talking about the smallest scale possible. Now, a mole is simply a large number of molecules, 6.022 times 10 to the 23rd to be exact. So when we say the word mole, we're just talking about this on the larger scale and just indicating the ratios that the molecules interact with each other. Okay, so let's do some practice. We've got a reaction here of zinc nitrate with sodium, producing sodium nitrate and zinc. And the, if you're given that in words, you would definitely want to formulate each of these formulas and start with that. But the first thing we want to do is make a tally of exactly how many atoms we have on the reactant side and the product side. So for zinc, as it is right now, we've got 1 atom of zinc on the left and 1 atom of zinc on the right. That's great. On the reactant side, we have 2 formula units of nitrate. So we have 2 nitrate ions in the formula for the zinc nitrate. On the product side, however, we only have this 1. So yeah, we don't see any subscripts. That 3 is part of the nitrate polyatomic ion. That's why I had to memorize it so that you recognize it as such. But over here, the nitrate ion is in parentheses with a 2 after it, so that's showing that there's 2 nitrate ions. Sodium, 1 over on the left, 1 over on the right, as is. So yeah, it's not balanced because those nitrates are not even. So what we want to do about that is, and let me kind of recopy the original tally. We had 1 and 1, 2 and 1, 1 and 1. What we want to do is adjust the coefficients up from 1 to 2 or 3 or any number that you think might help fix this problem of the equation not being balanced. And so because we are out of sync in our nitrates, we want to make sure we have 2 nitrates on the product side of the reaction. So basically I've just drawn in this 2 right here. So yeah, let's update the running tally. I haven't changed any coefficients over on the reactant side, so those will all stay the same. But by putting that 2 in front of sodium nitrate, I now have 2 sodiums and 2 nitrates. So problem is that I've fixed the nitrates, but it's still not balanced because now the sodiums are out of whack. So next thing to do is fix the sodiums, and let's kind of put our tally as to what it was before. We had changed that to a 2, and that had been a 1, and then when we put the 2 over here, the sodiums on the product side changed to a 2. So now actually we can balance this equation fairly easily. Just by adding this 2 on the sodium, I don't affect anything else besides the sodium, so that 2 can now be changed, that 1 can be changed to a 2. I've got 2 atoms of sodium represented in this equation now, and it's balanced, so that's great. Every 1 mole of zinc nitrate reacts with 2 moles of sodium to produce 2 moles of sodium nitrate and 1 mole of zinc metal. Okay, so just a couple quick tips for kind of how you approach this process. Definitely change the coefficients 1 at a time. Now maybe if you start getting really good at this, you can change them 2 at a time. But you want to see every time you change the coefficient from a 1 to a 2 or a 2 to a 3, you need to see how it affects everything before you go changing any other coefficients. Really good tip is that you want to first balance the atoms or compounds that only appear once on each side of the equation. So what I mean by that is in a very complicated equation, you might have carbon existing in multiple species being any reactant or product. So yeah, you want to start out with the ones that look like they might be easier to balance, because in balancing the ones that are a little bit easier, you might end up balancing the ones that exist in multiple reactants or multiple products. Keep your polyatomic ions together. I mentioned that this is this is part of why we had to memorize them, to be able to recognize them. Because usually you'll see them on both sides of the equation as a reactant and a product, and they haven't changed. Keep your running tally up to date, so every time you change one of those coefficients, update that tally. And I like to, rather than erasing, I like to just kind of cross out and write the new number on my running tally. It kind of helps me see where I've come from. And then hydrogen and oxygen, they're always good to balance last because oftentimes there's water involved in reactions. And so if you get everything else set, oftentimes you can just adjust the number of water molecules involved at the last step, and that will finish the process for you. So that's it for balancing and writing chemical equations, and I hope that was helpful.